Today I'm going to tell you about some joint work with Igor Pak in which we're investigating the problem of deciding if a Schubert structure coefficient is 0 or not. And this investigation is going to be guided through the structure of computational complexity. And so my goal in the talk is to show you how using the structure of complexity really led us to the right solution. Okay, so first let's talk about what these Schubert coefficients even are. We'll start in the flag variety. So I'll notate FLN C, right? And this is the space of all complete flags, where what that is I start with a 0 subspace, which is sitting inside of a one-dimensional subspace, inside of a two-dimensional subspace, and I just keep building up until I get to C. And we can naturally identify the complete flag variety with a quotient of GLN, right? Our complex valued n by n invertible matrices, where I'll identify some of these matrices if they're the same up to some certain row operation, where this B is the Borel subgroup of upper triangular matrices. And our B minus is just the opposite Borel subgroup, where that's just our lower triangular matrices. Okay, so what did I write the opposite Borel subgroup? Using the Bruja decomposition of GLN, we can write this as a union of these cells, where I can take orbits of these matrices. Okay, so we have this natural decomposition of the flag variety into these cells, which are called Schubert cells. And their Zariski closures are the Schubert varieties. Okay, so the Schubert varieties, which I'll notate XW, is exactly just the closure of one of these cells. So just stepping back, the flag variety naturally decomposes in terms of just permutations, where the permutations are telling you sort of the pivot structure of these underlying matrices. And when we take the Zariski closures of those cells, we get the Schubert varieties. And so this leads us to our main problems. Is we have these Schubert varieties, and a natural question is, how do they intersect? Okay, so in general, so we can think about the intersection problem of, I'll put that up here. So we can take a triple of permutations in Sn, right? This is over permutations in the symmetric group. And we can study the point count in the intersection of these Schubert varieties. So XU intersect with XV, intersect with XW, where I want this to be a generic intersection. So I'll translate these other two Schubert varieties by some generic matrices in GLN. Or in other words, I'm going to do some random change of basis, so that this point count is well defined. Okay. Now, just as an aside, we're going to want this to actually be a point count. I don't want to have some higher dimensional intersection. And so in general, when we're talking about these intersection numbers, we're going to assume that the dimensions are additive. So the dimensions of each of these Schubert varieties is computed by the Coxeter length of the associated permutation. And so we're always just going to assume, so that we really should have some number of points in this intersection, we're going to assume that their dimensions add up to the dimension of. All right, so for these numbers, we can ask how to compute them, right? And a central problem, right? We could just compute them geometrically, right? There are just some equations that are cutting out each of these Schubert varieties, and we could, just doing elimination, we could compute complex solutions to this system of equations, but that's not going to be very satisfying. So one of the central problems in Schubert calculus is to determine a manifestly positive combinatorial rule, or let's say algorithm, to compute these intersection rules. Okay? So by manifestly positive, I mean that when I'm summing up some number of weighted objects, I don't want any objects to come with negative weight, because then I would have some positive things that would cancel with some negative things. I just want to sum all the way, or we're just using positive weighted combinatorial. Okay. But this problem is very hard, right? Since it's sort of stating with Hilbert's 15th, right, to come up with some way to compute these intersection numbers without resorting to an algebraic elimination. Right, we have several rules that can compute these numbers in certain cases. So for the Littlewood-Richardson case, where we're talking about this intersection problem in the Grassmannian, this is solved using the Littlewood-Richardson rules, using puzzles, whatever. And then in some partial flag cases, this is solved. So for 2-step and 3-step, this is solved using work of Knudsen and Zentrostat. But outside of some of these constrained cases, we don't really have a general rule. Right? And so we could ask a coarser question of just determining an algorithm to decide if that intersection is just empty or not. Okay. Or equivalently, I could ask if the intersection is not empty. That'll be my favorite one. Okay. So is there any number of points in this intersection for one of these generic intersections? Okay, are the problems clear? Are there any questions about the setup? Okay, so I mentioned that we're going to be sort of walking through this problem using the structure of computational complexity. Let's see, if you're sitting in that corner, can you even see this? Okay. Can you see if it's in the shadow of the board above? Yes, okay, good to know. All right, so I'm not assuming that anyone knows any complexity background, so we're going to give a bit of a primer. So the type of problems that I'm interested in discussing this morning are all of a particular flavor. They're all decision problems. Okay? And this is a type of problem that we can classify in computer science, where these have just problems that have a yes or no answer. Okay, so are there some undergrad participants from last week in the audience? Yes, very excited. Okay, that's an example of a decision problem. Okay, and we could have much more interesting problems than just that, right? So here I have some ways that we can classify these problems in terms of their perceived difficulty as far as we understand them. Whereas we move up, this is a nesting of these classes. Okay, so at the bottom, we have P, which stands for, these are decision problems that we can actually decide outright if the answer is yes or no in polynomial time. Okay, so what's an example of a problem that's actually in P? I could do 2 coloring on a graph. Okay, so if I have a graph, you could ask, is that graph equivalent? Is that a bipartite graph? Or can you sort of walk along the graph so that you're always alternating in color no matter how you're walking, right? And you can do a greedy algorithm for 2 coloring, and so that's one way to see that this is in P. You could also have the problem of asking, is a Koska coefficient 0? I almost said very different. So is a Koska coefficient 0, right? The monomial, the coefficient when you're expanding a Schur polynomial into monomial, the monomial basis, right? And that's polynomial time as well, because that's just dictated by dominance order on those partitions. Okay, so these are problems that are in P, and that's sort of the easiest class that we'll talk about. But we can get into some more complicated classes. So NP, it stands for non-deterministic polynomial time. And these are the problems that we can check some evidence of a yes answer in polynomial time. Okay, so what is that? I could have not 2 coloring, but 3 coloring. So you can't do a greedy algorithm in the same way to overlay a random 3 coloring or a fixed 3 coloring on your graph. But if you claim that a graph is 3 colorable, how can you convince me that it is actually 3 colorable? You could give me a 3 coloring, and I just have to check it. Okay. Another one that you might be familiar with is just the Littlewood-Richardson rule, right? So you could have the problem of asking, is the Littlewood-Richardson coefficient, is that 0? Okay, and the Littlewood-Richardson rule gives us a way to test that this is an NP at least, right? Because I can just give you a tableau that I claim is counted by the Littlewood-Richardson rule, and you can check that it obeys all of the rules that a Littlewood-Richardson tableau should count, and then that would ensure that this was a positive coefficient. As it turns out, this is actually NP, but that part is much less obvious and is using some much bigger results. Okay, so we've gotten this high up, but there are much.
Sorry, is that equal to 0 or greater than 0?
I mean, you could talk about either.
Okay. Well, I thought it matters if it's like yes or no.
Oh, so sorry. Yeah. So that would be for the yes. Yeah. Thank you. But now that when you know it's in P, then it doesn't matter. But thank you for catching up. Yeah. Right. So as we work our way up, we can get much more involved classes here. Whereas right here at the next step up, these are the problems that we can check evidence of yes in polynomial time if we can peek at the answers to any 3 coloring problem in unit time. If we could check that for hints to our problem, then we would be in this class. And we can keep building up by saying that there's going to be a class above this that we could check evidence in polynomial time if we can look at the answer to any one of these problems or some hard problem of in here in unit time. And as we keep building this up, we'll build up to the polynomial hierarchy, which is quite large, but it doesn't contain everything, right? We have problems that are harder than that. And that gives us P space, which are the problems that I don't care how much time it takes me to decide the answer. I just care that I'm only going to consume a polynomial amount of space in my computer when I'm doing the computation. All right, so where is our Schubert vanishing problem in terms of the hierarchy? Sort of, if yes.
Where is the instance of NP?
And an example? Yeah, so you can talk about, I mean, a natural way that you can sort of build up is having an alternation of quantifiers in a SAT problem. So you can do like for all there exists 3 set. A lot of the natural problems here are sort of this flavor where you take an NP problem and then you add an addition.
Are there any of the inclusion known to be strict?
No. I mean, so all of these are strict inclusions, assuming some assumption in sort of. But so I will assume they're all strict for today, but proving any of these is strict, you'll get at least $1 million. Okay, so that is a good question. Right, so where is our Schubert problem lying presently in this hierarchy? So we don't have any combinatorial rule that we can just take off the shelf to get us an NP rule like we used for the Littlewood-Richardson coefficients. But we could look to some signed rules, right? We have different signed rules that can compute the Schubert coefficients. There's a rule of serrability that can compute with a sign. We could use a recursion of Allen-Knutson's that will compute the coefficients with a sign, or a different formula from Postnikov and Stanley. And using these sign rules will basically get you to P space, you can show. Okay, so somehow by using the structure of these formulas, doesn't matter how much time it takes, but I'm only going to take a polynomial amount of space on my computer as I'm computing these recursions. Okay. But that might not be necessarily obvious on its face. Okay, so this is where we're starting out. And right, this is pretty bad. Right, you would hope that you could at least get in PH using this breadth of combinatorial work that already exists, right? But just on its face, that is as good as we have it at the moment. Okay. And so we could ask what sort of problems or what sort of, this is a natural problem to discuss. And so what work sort of has already taken place in trying to actually attack this vanishing problem? So of course, many people have thought about this. Maybe I'll go up here and give the people in the mid. It's such a wide room. Okay, so what results do we know? Okay, so we have several combinatorial characterizations of this vanishing problem, but they're not both necessary and they're not characterizations. They're not both necessary and sufficient conditions for vanishing. Using something called descent cycling, so just looking at the structure of the underlying permutations that are defining these Schubert varieties, you can get one characterization of sometimes he can immediately tell you those coefficients are zero, sometimes he can immediately tell you that they're positive, but there is some unknown in between. You could look to use Ericsson Linnaeus permutation arrays, like Billy Vauquil did around 2008. That gives, it's sort of in the middle of a geometric and combinatorial characterization for when they're able to tell that the coefficient is definitely going to be zero in some cases. Okay, a bit later, again using just the structure of the permutations themselves and looking at the roots in relation. So Kevin Purbu came up with something called root games around 2003, where you set up some roots associated to your permutations on a game board, and it gives you some games to try to spread out some tiles, where if you can win the game, then you know that the coefficient is positive, for example. And in some cases, he can immediately tell you that it'll be zero. Okay, and last one I'll mention, you can use polytopes. So these polytopes that I'll call Schubertopes associated to the Newton polytopes of the Schubert polynomials, given by St. Dizier and Young, give another rule for when they can immediately predict that the coefficient is going to be zero. Okay, so this is just a little snapshot of some of the work that has gone into characterizing this problem too in terms of some combinatorial characterization. But the problem is you can't paste together these partial characterizations into a full one. That would be great if it was true, but it's not. But each of them is at least easy to carry out. Each of these gives, it would give a polynomial time certificate to check in the cases that it covers. Okay, and so we could ask, is it possible that the reason that we don't have one of these rules yet is because it's just provably hard, and that it would be absolutely impossible to get in any rule? Okay, that is a fear that you could have. And so, as you're sort of using the structure of this complexity theory, we could have a sort of optimist view, and a pessimist view. Okay, and in terms of what we think is actually fundamentally true about the problem. So if you're an optimist view, maybe this isn't even as optimistic as you could get, but we could hope that this problem is in NP. If maybe we're being optimistic, right? We're pretty far away from that as it is. So I would say that might be a bit optimistic. We could be even more optimistic and hope it's all the way in P. Okay, or we could be a pessimist, as Igor and I were at the start of it, and try to prove actually that this problem is sort of sort of pH hard, meaning that if you were able to prove that it goes any further than this, you would prove P equals NP. And so this is how we started out with using this complexity theoretic sort of structure. You have to sort of choose your target and chase it. And you don't know where you're meant to go because we don't know how hard the problem was to start out, right? And so we started with our pessimist view. And we worked for maybe a year and a half, and we were failing. And so, right, that sort of tells us that maybe the problem is easier than we thought, right? Anytime we thought we had a foothold into something that would be enough complexity to prove that it is actually hard, right, it would sort of slip away. There would be something nice that would ruin what we were trying to do. Okay, and so we can turn to the optimist view and trying to prove, even if we don't prove it's an NP, if we can get, anywhere better than this, that would already be better, okay? And so we started along this path, but it's hard to know what you should do because we don't have any combinatorial structure that will cover all of the NP, at least not on its face, okay? And so what structure do we know that we have in the problem? It's, as I mentioned at the beginning, we have some fundamental geometric structure, right? These coefficients are computing intersection numbers. And so how nice does that make the problem, right? Is that something that is immediately telling us why, or if we can't prove pH hardness? Okay, and so for this, we turn to a theorem of Colleen from 1997, in which he's showing that the decision problem, where the problem is if a system of, I'll say, small polynomial equations. So I have some polynomial system of equations, Fi's, where I don't want them to be too large to represent. So polynomial in size with respect to, let's say, there are n variables. So I want each of the coefficients to be small. I want the monomial support to be small. I want the number of polynomials I have to be small, so polynomial in n. And so the problem of deciding if a small system of these equations has a complex solution, he proved that this is in this class AM, which I'll tell you what this is, assuming the generalized Riemann hypothesis. Okay, so where is AM? AM is just out here. Okay, so if you know that your problem amounts to solving a system of equations that is small, it's not always trivial to see that the equations cutting out your intersections can be represented in an efficient way. But if you can do that, you get that your problem is lying within the second level here, which is a big improvement. I'm not going to say exactly what this is. This stands for Arthur Merlin, if you're interested. And this is a class of problems where these are problems where there's sort of interactive proofs, where you have a computer and an oracle that are passing messages back and forth, where you, as sort of the computer, are going to end up with the correct answer most of the time. That is a sort of very hand-wavy way to explain what this class looks like. And so Colleen was able to construct one of these interactive proofs to be sure that there is a complex solution most of the time. But he has to assume GRH. And he's using GRH to know that this test that he set up is going to be reliable, because he wants to do these checks over a finite field, and knowing that there exists a small enough finite field to do this over reliably is using effective Chebytarov density theorem. And so for that, we need GRH to be sure that that will always work. Okay, and so luckily, the Schubert intersections are in this sort of nice class. Okay, and that part was already done for us. So work of Heinz Satili is giving a really efficient system of equations that's cutting out these Schubert intersections, actually, from 2017. And separately, so that would be cutting out the intersection numbers that is characterizing a system of equations that's going to have a complex solution if and only if this coefficient is positive. But we could actually use work of Kevin Prabhu, where he's writing down another system of equations that's going to have a solution if and only if there is no point in that intersection. And so using each of these results, we get small systems of equations for both the original positivity problem and the zero problem. Okay. So we get that this is both in the class AM and it's in the class, and it's in its complement. So some evidence to check yes and some evidence to check no. That's what the prepending this code is. But we have to assume GRH again. Okay, so AM cap co-AM is still sitting over here. Now that we've added this intersection with co-AM, we're a bit lower in the hierarchy, which is great. But then you can ask, you know, where else do we go from here, right? Do we really think that this is the best that we can do? Do we have to assume GRH? Is there a way to remove that assumption, right? Because while it is intriguing, you don't want to have to assume, right? And so we're sort of gaining on this optimist view. I'm putting Stephen to work. We can sort of chase this optimist view and see what else the complexity theory can tell us for what we should hope for. And so what do I mean by that? So under even more complexity theoretic assumptions, so complexity assumptions of, in particular, strong de-randomization, you'll have that this intersection is actually equal to the intersection of NP and co-NP. Okay. So not only will you have one of these weird interactive proofs for both the yes and no problem, but you'll actually have an honest to goodness NP certificate and co-NP certificate. So an easy to check certificate of yes, easy to check certificate of no. And why do I think that this is so great to know? Because this intersection here is sort of, it's hard to find problems in here that don't immediately fall into P. So it's assumed that these are not equal as classes. Okay. But it is hard to find problems that are in this intersection that with a bit of extra work, you can't prove that it's just in P. Okay. An example of something that is actually in here that despite some people's efforts has not fallen into P is integer factorization. Okay. And it's very important to our cybersecurity that this does not fall. Okay. And so it would be sort of surprising to us if for some reason the Schubert vanishing problem was somehow in this elusive class, and that with a bit of extra elbow grease, we couldn't prove that it's in P. So that was our first hint that we should work a bit harder and see if we can get to a lower class. But secondly, us proving that we're in this class gave us a separate piece of, gave us another idea, really. Because in the natural flavor of this class is it's probabilistic in nature, right? You're not always going to get the correct answer necessarily. And so it sort of leads us to the question, what if we are okay with being wrong sometimes? And not that we like proving things that are going to work all the time, but what if we're okay with our algorithm being correct just most of the time? And what progress can we make with that extra flexibility? Okay, And so I'm going to sort of pause from talking about this Schubert story and talk about a natural problem that is of this flavor, where we have some sort of probabilistic way to solve this problem, but not a deterministic way. Okay, and so what is that problem? Okay, so let's take two polynomials. I'll have p in, let's say, n variables and q. And let's say it's just over a field path. We could just take over C, just fine. And we can ask, the problem is asking, is P equal to Q? Okay, perfectly reasonable. I have two polynomials. Are they the same? Okay. Now, first, I'll pause. And there are two different interpretations that you could have for this problem, right? What does it mean for two polynomials to be equal? First, you could say, okay, these polynomials are going to be equal if they're equal to 0 everywhere. Meaning that for every element of the field that I plug in, they'll always be equal. But I could have interpreted this question as something completely different, as something that we'll call polynomial identity testing. And what is that? For polynomial identity testing, I want them to have the same monomial support. Okay, so if when I expand the P and Q into their monomials, are their monomial supports exactly the same? Okay. And so I highlight this because this is actually a harder problem. Okay, you can check, right, that you can have a problem. This is maybe a fun undergrad exercise. Cooking up a polynomial where they're equal to 0 everywhere, but they aren't identical, depending on the field. You can play around to cook up one of these examples. And using this setup, you can sort of cook up naturally 3-sat inside of a special system like this over F2. Okay, so we're going to go with the PIT formulation of this problem, where I want to know, are these polynomials exactly the same? Are their monomial supports exactly the same? Are they identically the same? Or in other words, if their difference, let's call P twiddle, P minus Q, is identically 0. So often you'll see this problem formulated as just asking if a polynomial is identically 0. And you might say, okay, that seems like a pretty trivial problem. I'll just walk along the monomials and cancel as I see the monomials canceling. And if I end up with nothing at the end, then it's 0. Okay, but the problem is the input size. We want our input size to be measured in the number of variables. Okay. And I could have a really big monomial support, and it would take me too long to read over the entire thing. Okay. I could also have my coefficients absolutely blowing up in the middle, because I could have Google many plus x1s and then Google many minus x1s. Right.
Are we matching that these polynomials represented in standard form, or might they be like some product of things?
We're going to be okay with even black boxing, having some. Yeah, so that's a good question. So in terms of how we're sort of interpreting these formulas, note black boxing is okay. And so what do I mean by that? Right, I can take the determinant of some matrix of variables. And if I'm expanding that determinant in terms of the monomials, right, I'm going to have factorial many terms. But if I'm just storing this as, I'm just saying this is the determinant of this matrix, whatever that ends up being, then that takes much less space in my computer. And so this sort of representation is going to be okay. All of my input size is going to be really measured in my variables. Other questions? Okay, so for this PIT, how to solve it? Okay, if I give you a random polynomial and you couldn't go to the coffee break until you decided if it was 0, then what would you do?
See if it has more roots than it should.
See if it has more roots than it should. So what you're saying is you maybe just start plugging in things and see if it's always 0. Okay, so let's just take a random entry, a random vector, and I'll plug it in. And so if when I plug in, let's say I'm plugging this into P twiddle, if we don't get 0, right, then I know with 100% certainty that it's not 0. Okay, and if I do get 0, then two things can happen, right? Either I was identically 0, or I accidentally found a root. And so when I'm analyzing this problem, right, it doesn't take me that long to plug it in. That is polynomial time for me to compute. And so now I just want to look at what is the probability of this bad thing happening. Because if I accidentally sampled a root, I might be fooled into thinking that this was 0, even though it was not. And so if we're thinking about our failure rate, we just have to compute the probability of finding one of those roots. Okay, and luckily we have a theorem for that. So I can do that. And this is a lemma that you might even see in an undergrad probability class. To prove it, you just need some elementary probability and the fundamental theorem of algebra. Okay. So for this, let's take a polynomial that is not identically 0 of degree d. Okay, and let's select entries, let's say R1, to plug in to this polynomial, R1 to Rn, randomly in a set S. So I'm going to generate these random choices uniformly and independently in this set S that I've already set aside. I just set aside a set S to choose what to plug in from. And the lemma says that the probability of accidentally sampling a root, so I plug in R1 to Rn for my variables, and the probability that I accidentally get 0 is bounded above by just S d over S. I just take the degree and I divide it by the size of the set I'm sampling from. Okay, so this tells me exactly that if I'm trying to bound, right, how often I find a root, if I choose a set big enough to sample from, I can make this probability of getting a root as small as I want. And so what does that tell us about PIT? As a corollary, we get that we can decide if a given polynomial is not identically 0 in probabilistic polynomial time. Okay. What I mean by that is in polynomial time, we can output yes or no, where in fact, we're only going to, if we output yes, then we know by this algorithm that 100% of the answer is yes. And if we output no, then there's a small chance that we could be wrong. Okay, and this class is called RP. So this is really proving that the negation of PIT is in this class, RP. Where is RP? It's here, sitting below NP. And so as a corollary, we get the negation of PIT is in NP. What is our certificate that the answer is yes? It's the things that we generated that we plugged in where we outputted some non-zero number. That is our certificate. Okay.
So if you're plugging stuff in, aren't you doing like easy E and not?
Well, that's the thing, is we don't have to check everything. For easy E, we would have to check every evaluation is zero. Because easy E is that every evaluation of any vector in Fn is zero. And we're just checking that it should be zero everywhere because it's identically zero. So we're doing a rough check of this, and that's why it's just probabilistic. And this gives some intuition for why easy E is harder, because we can't plug in everything, right? Plugging in all of my roots isn't going to really tell me anything if it's not identically zero, but just based on the field, everything will be zero. Okay, so now we've seen examples of some of this probabilistic structure, and so now I want to apply it to the Schubert problem. Okay, so how can we think about these Schubert coefficients as, right, being non-zero if and only if I have some polynomial is identically zero. And so you might be tempted, let's see, oh, let me go here. Okay, we could take the Schubert polynomials of Lescu and Schutz and Berger, and by the Borel presentation theorem, I'm just erase the variables. By Borel presentation theorem, their structure coefficients are exactly going to be the Schubert structure coefficients, where I'm going to have an extra twist based on my formulation. Where these are Schubert polynomials. Which are the polynomial representatives of the Schubert classes in the cohomology of the complete family. Okay. And so you could hope that you could use the Schubert polynomials in the Schubert expansion, right? These are polynomials. And if I know what each of these expansions are, then, right, if I'm wondering if I have the correct coefficient here, these are an integral basis. So there should be a unique way to write this expansion. Right? And so I could just ask if I'm given this, and I could just check if these are equal. But we can't do that. Okay, and why can't we do that? I don't have an efficient way to write a Schubert polynomial. They have exponential monomial support, and I don't have a nice way to black box them. So we can't do this, as tempting as it is. So we have to do something else. And luckily, Kevin has just the lemma for us. In 2006, in which we'll take these vector spaces that are corresponding naturally to some root spaces, where I take the Lie algebra of nilpotent n by n matrices, so strictly upper triangular matrices, okay? And I'm going to intersect with something sort of technical, and I'll tell you sort of how you can think of it. So this is all a Lie algebraic statement, where this is the Lie algebra corresponding to the opposite Borel subgroup. right? And this is just the permutation matrix corresponding to, if we have row, it's just a permutation. Okay. How you can think of this is I'll have my strictly upper triangular matrices, and I'll have a free variable corresponding to every inversion of that permutation. Okay, that's going to give you some vector space of matrices. And so using these matrices, he gives the statement that your coefficient is going to be positive if and only if, where I take the adjoint action of some generic GLN matrix on these spaces. U. So for generic matrices A, B, C in GLN. So I cook up these root spaces, which I have an explicit way to construct combinatorially. I act on these matrices by some random GLN. And what this statement says is this coefficient is going to be positive if and only if this sum of vector spaces is actually a direct sum. Very explicit. Okay. And in fact, if we place the additional assumption, that should be placed if I'm talking about this Schubert intersection problem, right? That the dimensions should add up. Not only do I need it to be a direct sum, I can say something even more precise. This should be the space of all nilpotent matrices. And so to obtain this, he's really turning this question of looking at these intersection numbers to checking that these are the tangent spaces of these Schubert varieties are intersecting transverse. And that naturally, under the killing form, is translating these problems from the Schubert varieties to the tangent space to vector spaces. And this becomes linear algebra. Okay, so what we do is the following.
Sorry, Colleen, are ABC, are they in GLN or are they in like the?
They're in GLN.
Okay.
Or sorry, I think
Not in
I might want them to be unipotent actually.
Okay.
So. Thank you. That is exactly right. Okay, so what we do is with Igor, we construct a matrix, an explicit matrix. It's going to be n choose 2 by n choose 2, pretty big matrix, MUVW, such that my coefficient is going to be positive if and only if this matrix is non-singular. Okay, but the matrix being non-singular, right? This means that the determinant is not identically 0. That's what it means for me to have my my vector space being too low in dimension. And so this is a PIT problem, right? I have an explicit matrix, and I just want to know, is this polynomial identically 0? When I write out everything in this determinant, does everything cancel? Okay, and so then we appeal to PIT. And the zip lemma, right? Because I want to know, I have my matrix. I don't want to write everything out. So I randomly sample points and test if I output 0 every time. Zip lemma tells me the probability of me accidentally making the matrix singular when I'm doing these evaluations. And we get our theorem. We get that testing, our Schubert vanishing, or Schubert positivity, is in RP. No more GRH, no more anything. We get an honest to goodness probabilistic polynomial time algorithm to decide if there is any point in that intersection. Now, the great thing about Kevin's lemma it really doesn't depend on type and it doesn't depend on how many intersections we were taking. So this result actually extends to arbitrary type, A through D, and arbitrarily many intersections. So maybe you care about 5-fold intersections instead, and this works just as well for those. Stop there.
Thank you for this great talk. Are there any questions?
So you said it works for like 5-fold intersections, but what if I take like log n?
Yeah. So we are going to just assume that each of, none of the Schubert varieties that you're intersecting are trivial. So none of the permutations are the identity permutation. And so as we're reading, the list of permutations, each of them should have dimension, each of those varieties should have dimension at least 1. And so once we've read n choose too many, if we read any more, we automatically know it's 0 because the dimension counts.
Can you make any statements about whether or not an equivariant coefficient is non-zero?
Not, no. So that would be maybe something to do in the future. But these techniques don't necessarily immediately extend to that set.
Do you see a way to like extend this to answering problem 1?
Yeah, so that is also some things we're currently thinking about. So it is the case that sometimes you can adopt these probabilistic algorithms to probabilistically count and sort of approximate sizes of sets. And this would be good.
No more questions. Let us thank Colleen again.